Hey, you guys, today we are going to start to talk about limits, which seriously makes me really excited. I don't know if it's just because I love Mean Girls, the limit does not exist, or if, well, no, I really do just enjoy limits. As I said before, this is truly the bridging topic into calculus for those of you who will move on to calculus at some point in time, whether, next year or in the future. So you'll definitely want your graphing calculator. Again, if you have not yet accessed it on your school device, I have information under modules on how to do that. If you still don't have access to a graphing calculator, if you can't get, school access, you don't have a school device or you don't have your own, then you can always go to desmos.com and you can work from there. There's also a phone app called Calculator X, which looks very, very similar to the school calculators you're used to, but it's technically not TI. So you could download that phone app, Calculator X. I will show you my calculator up here on the screen throughout the lesson. And so you can also follow along that way if you'd like. Obviously, that's not going to help you for practicing purposes later on, though. There are two different documents linked on here for blank copies of the notes if you would like to pre-print them, or you could just take notes on any notebook paper you happen to have. So here goes. I'm going to switch around my computer. Let's do it. So, like I said, there are three ways we can find the limit. Analytically, which means the old paper and pencil, like I'm just going to do the algebra only using my calculator to help me do, basic math calculations. We are going to focus on finding limits analytically next week. Today and our next meeting, we are going to find limits numerically, which means by a table. Table would be the numerical approach. And then finding limits graphically, which definitely makes sense looking at the graph. As we said, or as I explained in the live Google Meet that we had, we know that finding a limit is really our best estimation or our best guess of what is happening in a situation where we can't truly see what's happening. Think about if your internet buffers and you miss a split second of whatever video on YouTube you're watching or whatever athletic event you are watching on your TV. You can make really good guesses as to what happened in that split second that you didn't see. And you make that decision as to what happened in that split second you didn't see based on what happened before and what happened after that split second you did not see. So we're going to use the same idea, both numerically, table approach, and graphically. We're going to make an estimation as to what is happening at a certain point based on what happened before that point and what happened after that point. So we are going to go with the numeric or the table route first. So I've already actually put this rational function into my graphing calculator. So if you need to, pause and go ahead and put this in your graphing calculator. And we want to know what appears to be the value of the function as x gets closer and closer to 2. Now, here's the key word, appears. Many of you will say there is no value of the function when we plug in 2. If I find f of 2 and I plug in 2, we can see already in the denominator 2 minus 2 is 0. I don't really care what happens in the numerator because anything divided by 0 is undefined. F of 2 is undefined. And here's a big difference. Limits are not asking what is the value of the function. The value of the function, undefined. We can't divide by 0. We want to know what appears. If you blinked at 2, what would you expect to be happening at 2? Again, a limit's not what is happening or not necessarily. It could be what's exactly happening, but what would you expect to be happening at 2? So again, go ahead and we're going to put this function into our calculator. And we're going to fill in this table. You will notice that, and you know what? I'm actually going to cross out 2. I don't care what happens there. I'm not even going to put undefined because I don't, your calculator is going to say error, but I'm not even going to put anything here because I don't care what's actually or what's not happening there. I'm going to use what happens before, pretend I blinked at 2, and what's happening after to make my decision of what I would expect to be happening at 2. So I picked numbers before 2 for you, and I picked numbers after 2 for you already. And the next example, we'll talk about how do I choose these numbers right here. So going to my calculator, I'm actually going to go to my table. And actually, I'm going to hit second window, and I am going to put my table, my independent on ask, so I can type in whatever I want. And on table, I'm going to type in 1.75, and I get 18/25. If you want to turn this into decimals, if your calculator is doing mine is doing, I am going to go down here under mode is what I hit. Whoops. I'm going to go down, 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 down. You'll see down here answers goes to auto. I'm going to go to decimal. Decimal usually makes it a little bit easier to make decisions. So 1.75.72. 1.9. We are at 0.9. I shouldn't have typed right over that one. 1.99. We are at 0.99. 1.999. We are at 0.999. So coming up to 2 from values less than 2, this is less than 2. Anything less than 2, it looks like I'm getting closer and closer and closer. The 0.999, approximately 1. Well, let's see what happens after. I'm actually going to start at the end with the 2.25. Whoops, I got an extra 5 in there. And we get 1.25. And down to the 2.1 is 1.1. 2.01 is 1.01. And 2.001 is 1.001. Okay, and I'm going to switch back so you can see my notes right here. So I filled in based on what we got in our calculator. And again, limits are not asking what is happening at 2. I already know nothing is happening at 2. But if I had to guess based on what happened before and what happened after 2, a limit is asking the question, what would you expect to be happening at 2? Well, based on this, I would expect to see the number 1 at 2. 0.999 and 1.001. It looks like everything is building up that I should have the number 1 in here. Okay, well, how do we look at this graphically? Again, I'm going to go back to my calculator. I already put it in my y equals. I am going to set my window based on what I see on the notes. My x min, I'm only 1 to the left. My x max, 1, 2, 3, 4. Scale can stay. My y min, -1, 1, 2, 3, 4, 5, and my y max of 5. And I'm going to hit graph, and I am going to sketch this graph right in here. And you will notice, and I'm going to do my best try. I don't actually have a ruler here at home. Go figure. We noticed it looks like a line. Now, it looks like a line, and based on our calculator, even though we know nothing is happening at 2, our calculator doesn't show us that. If you remember, at 2, that should technically be a hole, but our calculator doesn't. We can't see that in this case. If we zoomed in further, we might be able to see it. So how do we find a limit graphically? Again, we're going to take the same approach here. What's happening before we hit 2? What's happening after we hit 2? So I like to take both of my fingers and I place them on the graph, or you know what, instead of my fingers, I'm going to just use tips of my pens here. And I put them on either side of the graph, less than 2, because 2 is my point in question, and greater than 2. And I am just going to slide closer and closer to 2. But frankly, I don't care what is happening at 2. I just want to squeeze 2. So if I squeeze 2, I'm going to answer the question, where would I expect for both sides, my fingers or my pens, where would I expect them to meet up? At what y value would I expect them to meet up at? Well, in this case, I would expect them to meet up at a y value of 1. Putting this into limit notation, this is what limit notation it is. Limit notation, LIN, stands for limit. It says the limit of my function, and I put the definition of my function right here, as we approach an x value of 2. So, sorry, my kids are walking in here. Go ahead and close the door. The limit of my function, or what would I expect my function to be doing as I get closer and closer to 2, I would expect my function to be giving me a value of 1. True limit notation. What would I expect to happen? Not necessarily what is happening. Okay, so moving on to another example, I want you to go ahead and stick this one in your calculator. And I am just going to turn this one, clear that one out. I have mine in already. And we're going to build a table. So how do I choose? Notice in this case, I want the limit of this function as I get closer and closer to zero. So in other words, I want to know what would I expect to be happening at zero as I approach from numbers less than zero and numbers greater than zero. So I'm going to put that in here again. This side's going to be less than, this side is going to be more than zero. Frankly, I don't care what is happening at zero. In this case, it would be another undefined. I just want to know what would I expect to be happening there. So if I think about numbers that are more than zero, I could put 1, 2, and 3. And although 0 and 1, if I put a 1 here, are technically pretty close together, there is still so much space between 0 and 1. We want to be close to 0 without leaving too much wiggle room. So I would probably put the next integer as the largest number. And I'm going to mirror that as the less than, and I'm going to try and use decimals to get me closer. Now, if you choose numbers and you're like, hey, that's not really helping me make a really great decision, then you could always pick numbers that are even closer to zero, that are squeezing zero as much as possible. So I'm going to go down to 0.25. Mirroring it, that would be negative 0.75, right? No, negative 0.25. Wow. And let's say 0.1. So this would be negative 0.1. I could put the 0.25 here, 0.1, 0.001. I could do something very similar to what we did up here. This is really up to you. And again, if you cannot make a decision based on the numbers you chose, then pick numbers that are getting even closer to zero, You always want to use decimals though. You don't want to make everything integer values because that leaves you too much wiggle room. So using what I just chose, I am going to go to my table. And here we go. I got negative 1. I'm going to type over what I had there. That gave me 1. Negative 0.25. That gave me 1.866. If it's too much to look at all the other stuff too, I'm going to go ahead and delete it rather than type over it. Negative 0.1 gives me 1.9487. Is it super important to put in all those decimals? No, you're using these to help you make a decision. So exactly what those decimals are, not as important. 0.25, 2.118, and 0.1, enter, gives me 2.0488. In this case, from numbers less than 0 and numbers then greater than 0, if I look at what they are approaching on either side, I would say they are leading me to a number, the number 2. Now, I guess you can't see what I'm typing at. If I have a tough decision again if it's tough for me to choose that they are getting me closer and closer to 2, then type in 0.01, negative 0.01, 0.001, negative 0.001, and see if it's still squeezing 2. In this case, it does look like it is leading me to 2. Now let's verify this graphically. I'm going to go to my window, and let's see, I am at an x min of negative 2, an x max of 2, y min, I'm going to leave my x scale alone. Y min of negative 1 is okay. Y max of 3. I'm going to graph, and I'm going to sketch this right onto my notes. So here we go. So again, I want the limit as I get closer and closer to 0. And we know it isn't as x approaches 0. So here's my x of 0. And I am going to take my pens and I'm going to jump on my graph on either side. Now notice my graph doesn't exist over here. So I'm going to jump on where it exists. It's okay if it doesn't exist over here. As long as I can jump on the graph to the left of 0, it doesn't matter where I jump on. So I'm going to jump on the graph and I'm going to get closer and closer and closer and closer to that x value of 0, not actually getting there. But I am going to ask myself, what would I expect to be happening there? Where do I expect my graph to be leading me? Where would I expect these two pens to meet if they were to hit an x value of 0? Well, I would expect them to meet at a y value of 2. So we say the limit as x approaches 0 of my function. I'm going to just call my function f of x. You can put a function name there, or if it was named, I'm going to name it right here. Or you can put the actual equation. So the limit of my function as x approaches 0, it looks like my function is taking me to 2. Technically speaking, again, there is a hole right there, but it looks like my function is leading me to 2. So let's do a couple more examples. And I am actually going to jump to number 4 on this second document. Things, again, I want you to recognize and realize. Again, the value of the function is different than the limit of the function. Could they be the same? Yes, they could be the same, but they do not have to be the same. And one's existence means nothing about the other. So this says find the value of the function for each a value and find the limit as you approach each a value. So first, we're going to go with what is f of -3. So what is the value of the defined point at -3? Well, at -3, my defined value is 4. I have a filled in point at 4. I'm going to go ahead and do all of these. At -1, what's my defined value? Well, at -1, I have my filled in point at 3. F of 2. Well, at f of 2, notice, do we have any filled in points? Nope. The value of the function is undefined. There is no defined point. And f of 4, going over to 4, f of 4 is 5. So now that we have all of the actual defined values, now we're going to go through and find the limit. But before we do that, we are actually going to jump to the last page of these notes right here. As those of you who have seen Mean Girls know, the limit does not exist. There happen to be cases where you cannot find the limit, and there are 3 reasons why that could happen. Now, I would highly suggest that for each one of these, or right now, you pause the video and you sketch these graphs in here yourself rather than just take it for what I give you. But you can count the window based just on the tick marks. This is a picture of your calculator screen. I am going to sketch each of these in here, and we are going to talk about why the limit as x approaches 0 does not exist. Or we're going to talk about the 3 cases where the limit does not exist. So for this first one, this absolute value rational function, the graph happens to look like this. And we say that the limit of the function, I'm just going to name it, use its name, as we approach an x value of 0 does not exist because, and here's why. I'm going to use the graphic approach. I would highly suggest you also go in your calculator, look at the table, and see if the table backs up the graphical approach. They will or should always back each other up. But we know if I'm going to find the limit, I want to jump on my graph on either side of my x value in question, 0, and I am just going to approach that x value of 0. I'm not actually getting there. I don't actually want to be at 0, but I'm going to now ask myself, now that I'm really, really close to 0, where would I expect the function to lead me? Well, if you notice, down with my pink pen, I'm approaching a y value of -1. With my blue pen, I'm approaching a y value of +1. In this case, we say the limit does not exist because when I approach my x value of 0 from the left and I approach it from the right, I'm being led to 2 different places. A limit cannot be 2 different values. A limit should be 1 value where the two pens in this case are, or we're expecting them to meet up. In this case, being at -1 and +1, I don't expect these pens to meet up. And now I can't make the choice and say, well, the limit's -1 or the limit's 1. There's nothing leading me to one end or the other. So we say the limit does not exist because the graph, or because I should really say, and put it this way, because the function is approaching 2 different y values. 2 different y values. Case 1, where the limit does not exist, we are approaching 2 different y values. Okay, Case 2, again, if you did not already pause and explore this in the calculator yourself, I would highly suggest doing that. I'm going to just sketch in my graph here. And again, we say the limit for our function, which also happens to be called f of x, as we approach 0, does not exist because, here we go. Again, I would highly suggest you backing this up with the numerical or the table approach. But graphically, I am going to hop on my graph on either side of 0. And I am going to just follow my graph. And I'm going to ask myself, where am I being led? Where would I expect these two pens to meet up? Well, hopefully you recognize what's happening here. This is a vertical asymptote, which means my graph is just going up, up, up. Yes, it's kind of inching closer and closer to that y-axis, but an asymptote is an imaginary line that we are never going to touch or cross. So are my two pens ever going to meet up? Technically, no, because we can't cross over that asymptote. Now, you may say, well, my pens are going to infinity. Infinity is technically not an acceptable answer for a limit because infinity is not a concrete place. It is an idea. So we say that the limit does not exist because we are approaching, because the function approaches a non-real number or an idea. Infinity is an idea. It is not a concrete place. If you cannot say, hey, this is the value on the number line that we're getting really close to, then you have to say that the limit does not exist. And here we go, case 3, my favorite case of why the limit does not exist. Please, 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 if you're just like, I'm waiting for Mrs. P to put it in the calculator, this is the best one yet. And looking something like that. So for this one, again, we say the limit of my function as we approach an x value of 0. Do all of these examples happen to be approaching 0? Any of these 3 cases could happen regardless of what the x value is. We say that the limit does not exist. And by the way, yes, this is official acceptable calculus shorthand. This is not Mrs. P is just making it up because the function, I like to think of this as the freak out mode, or it can make up its mind. Whoop, I spelled because wrong. Because the function is oscillating between two y values. This typically happens with trig functions, as you can see, or in some trig function cases, not all trig functions. But this typically doesn't happen unless you are using a trig function, but it could. Never say never, right? So again, if I jump on this graph with my 2 pens and I get closer and closer to 0, all of a sudden I'm doing this. So how do I say, oh, I'm going to a y value of 0 or I'm going to a y value of 1? I can't. My function can't make up its mind. My calculator can't make up its mind. So we're not going to make up our mind. The 3 cases where a limit does not exist, you are approaching 2 different y values. You're approaching an idea, so any infinity, or the function is oscillating. It's freaking out. It can't make up its mind. So going back to this example, and this will be the last one we finish up. I'm sorry if this video is getting a little on the long side. Here we go. We found the actual defined values of each function, but now we're going to compare them to the limits at those indicated a values. So here we go. I'll do this down here. The limit of our function as we approach the value, we're going to use -3. Here we go. I'm going to find -3. I'm going to jump on my graph on either side, and I'm going to get closer and closer and closer and closer to -3. Once I'm super close to -3, like at that -2.999 or -3.001, I'm going to say, okay, where are my pens meeting up? And you'll notice my pink pen is up there. My blue pen is down here at a y value of -2. My pens are not pointing at each other. They are in 2 different places. So this is actually case 1. This is the limit does not exist. Do we need to identify which case? No, the limit does not exist because in this case, we happen to be in 2 different places. Okay, part B. Here we go. The limit of my function as we approach an x value of -1. Locate -1, jump on the graph on either side, and we're going to approach -1. And right when we're squeezing -1, we're going to say, okay, are my pens being led to the same point? And in this case, I'd say, yeah, both of my pens happen to be squeezing this circle, which is at a y value of 1. Now notice, in both case A and case B, the defined value of the function does not match up with what the limit is. That is A-okay. The definition of the function, the defined point of the function, and the limit do not go hand in hand. They do not have to be the same. One does not have to, one's existence means nothing about the other. Defined point is where is it filled in? The limit, where is my function taking me? Or where would I guess my function is taking me? Again, think about that example of if your screen was to buffer and you missed something, you're using what happened before and what happened after to make your best guesstimate of a point that may or may not actually be able to be observed. Okay, so part C, we'll do part C this way. Limit of my function as x approaches, that was an arrow, 2 is. So find an x value of 2, jump on my graph on either side, get closer, 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 closer. And yeah, my pens are squeezing the same point. Similar to the last one, they happen to be squeezing a y value of 1. My limit is 1. So something else we notice, could multiple limits of the same function give the same value? Heck yeah, totally can. And last but not least, part D, the limit of my function as we approach an x value of 4 this time. Whoops, my equal sign should go up here. 4. I'm going to jump on my graph on either side. I'm going to approach the x value of 4. My pens happen to be pointing at the same place, and they happen to be pointing to a value of 5. Now, in this case, the defined function and the defined point and the limit happen to be the same. Again, the value of the function, the limit, one means nothing about the other. They can be different. One can exist, the other doesn't have to. They can be the same, but they do not go hand in hand. So there are a ton of other problems that happen to be on the notes. I will have the answers in my PDF of the answer key, which you will be able to find here on Canvas. There are also some practice problems, which are listed out on the first link of the notes available in your book. And I wrote out where odd answers happen to be. I will see you next time, and we'll do a little bit more practice on this.